Okay, class, welcome to lecture 15. Today we're going to be doing more of what we did last time, but now we're going to put some fancy language on top of it. So technically speaking, we're going to be talking about the sampling distribution of the sample mean, but actually we already talked about that last time. Oh, my Apple Pen is not working. 1 second. Okay, back on track. So we're going to start off with some notation and some jargon, so very fancy things that math people like to use to make things seem extra confusing. But it's just related to what we did last time. So the normal distribution that we found last time, remember how we did that? We get all possible sample means. Well, that has a fancy name. So the sample distribution, the normal distribution you get by finding all sample means is called, the title of this section, the sampling distribution of sample means, or of the sample mean. So that's the first bit of jargon. And then we're going to use our big X, little x notation that we used a while ago. So big X with a bar on top of it is the random variable associated to this distribution. So don't worry so much about that right now. But the idea is that the sampling distribution goes along with the random variable, and the random variable, remember, takes possible values that you call little x, but it's going to be little x with a bar on top of it. And so these are just the possible sample means that you could get. So we've sort of already done this stuff last time. We just didn't say all these fancy words. So little x can be all the possible sample means that you could get. And then a little bit more notation. The sampling. So now what we could do is we could call this the sampling distribution of big X bar, because big X bar is the random variable associated to the sample mean. But now this distribution, remember last time we said that it's just some bell curve, and it has the mean being the same as the population mean, but that mean has its own fancy name. So it's called mu with a capital X bar as a subscript. And it has a standard deviation because it's a normal distribution, sigma with a big X bar as a subscript 2. So really what's going on is that's the middle of this distribution that we get, and then the first inflection, the inflection points come from using that standard deviation and adding it to the mean to get the one to the right, or subtracting it to get to the one to the left. But we technically, again, we did this stuff last time. We just didn't say it with this fancy language. So we'll mix it in when we do more problems, and we'll see it's not so bad. So then, yeah, so what we did last time is what we already know here, that this mean is always going to be the same as the population mean, which is mu. So this is the mean of the population. That's what we used last time to draw these things. And we also know that this standard deviation, how did we find this? It was always just the standard deviation of the population divided by the square root of the sample size. So we already used this stuff, we just didn't call it this thing. So this is the standard deviation of the population, and this n is the sample size. Okay, so now let's do examples like we did last time, but with this new jargon in place, just so we can see how it all fits together. It won't be so bad. All right, so it's going to be very familiar. That way it's not overly complicated. We'll use the IQ example. So IQ is normally distributed with mean mu 100 and standard deviation. So this is our population mean and our population standard deviation. And remember that the distribution that we're creating is not this one, it just comes from this one. Comes from using these two numbers. And the fact that this is normally distributed is not necessary. It just happens to be true in this problem. Okay, so now we can do questions like this, like we did last time, but using find the probability. So now we can use this new jargon. Find the probability that a random sample of size, let's say 20, has sample mean between 102 and 105. So we did stuff like this last time, but now we're going to introduce some jargon, and then I'll do a second part just to compare. Find the probability that, so this is no longer about samples, but a randomly chosen person, just a single person, has IQ below 105, just to compare these two different types of questions. Okay, so start with A. So the idea is, since the population mean is 100, that tells us that the mean of the sampling distribution of the sample mean is also 100, because those are the same. And the standard deviation being 15 of the original of the population tells us that the standard deviation of the sampling distribution of the sample mean is going to be 15 over the square root of the sample size, which is told to us up here is 20. And this we can estimate 3.35 roughly. So now we can build that normal distribution that we built last time, but now we'll put the fancy name on it. So the sampling distribution of the sample mean X bar is, and now we're just saying it in a very fancy way, is this distribution, where this is 100 in the middle still, but now the first inflection is at 103.35 because I've added one standard deviation, and I'm subtracting the same amount. Can't do that in my head though, so there you go. So then the idea is that possible values of the sample mean are just these numbers along the x-axis. And so those are what little x is. Because remember, possible values of big X is called little x. So little x are these numbers along the x-axis, and they appear with probability according to the bell curve is the idea. Okay, so now we want to know, to rephrase this question, so we want to know the answer to this, but now we're rephrasing it with fancy jargon. We want to really know the probability of big X bar being between 102 and 105, but that just means that we need to find the area. And again, we did this last time, this kind of problem last time, but now we're using fancy terminology. Okay, so how do I find area between 102 and 105? I'll just sort of estimate 102, 105. How do I find this area? Well, that's when we use our z-score stuff, which we're pretty used to by now. So we need the z-scores for, so the idea is that these little x bars are what big X bar can take values of. So now we're looking at two specific values. We're looking at 102 and 105. So because there's two values I'm looking at in this problem, I'm subscripting with 1 and 2 to distinguish between them. Okay, so I need to get two z-scores, one for each of these. So the z-score formula is not going to change. It's just the data point on the distribution, so in this case 102 for the first one, minus the mean of the distribution over the standard deviation of the distribution. So this looks very fancy, but this is just what we've done before, where now I know 102 is the data point, 100 is the mean, and I know that this 3.35 is the standard deviation. So I just do 102 minus 100 over 3.35, and I use a calculator, and it'll turn out to be 0.597. And then I do the same thing with 105, but now I'm just using this very fancy language. So x2 for z2 minus the mean over the standard deviation of the distribution. So 105 minus 100 over 3.5. This will be 1.49. So those are my two z-scores. So now I can plug those z-scores into that online calculator to find various things. So if I plug the z-score in for the first one, it'll get me this red area. If I plug in the z-score for the second one, it'll get me this green area. So if I want to do the blue area, I just got to do the green, and then I got to take away the red. And that'll be the blue area left over. So that's all we're going to do to finish the problem. So then let's do that. Let's see. So online calculator will tell us that there is, let's see, 0.724 area to the left of the first z-score. And if you do the other one, 0.932 is what you should get. Area to the left of the second z-score. So then I just do, so if I want to get the area between the two, I just subtract. And you'll get 0.208. So then to answer the question, in context, the probability of a random sample of size n equals 20 having sample mean between these two things, between 102 and 105, is 0.208. Okay, so now for part B, we're not dealing with samples anymore. We're just dealing with IQs, and this only works because IQs are normally distributed. Otherwise, you wouldn't be able to use this bell curve stuff. So now we're not looking at this other distribution, we're just really looking at the original one. Coming from having mean 100 and standard deviation 15. And then we're looking at area below 105, I believe. So 105 is about there. So now we're really just looking at this area. And so you only need the z-score for 105 on this distribution. We get 0.33 repeating. And if you use the online calculator, you'll get the area to the left to be 0.630. And then that's going to be your answer, which you can put in context. Okay. So that's how we introduce some of the jargon. Now we're going to introduce a bit more. And sort of do the same thing where we do a problem that we already know how to do, but now we're going to add in the jargon that we just learned. Okay, so a parameter is secretly what we've been talking about already, but now we'll give a name to it. A parameter is a number associated to a population. So the population mean of IQ scores being 100, that would be an example of a parameter. A statistic is a number associated to a sample instead. So a sample mean that you get is a statistic. Okay, so now we'll see more examples, and I'll introduce this language in the example we do right now, just to get more used to it. Okay, so here's a new distribution. The length of human pregnancies is normally distributed. Again, it doesn't have to be. The point is that the sampling distribution that we create afterwards will automatically be normally distributed, which is good. But in this situation, we also have that the original population is normally distributed. The original distribution is normal. okay, with mean 266 and standard deviation 16 in days. Okay, so now let's bring in this new jargon that we just learned. So here, what's the population? The population that we're studying is human pregnancies. And the parameter, the number associated to this population, is the mean number of days of a human pregnancy. So we're associating a number to the population of human pregnancies. And that number is just the mean. We're looking at the mean number of days of a human pregnancy. So this is given to us, it's 266. That's the number associated to human pregnancies. It's the mean number of days, so it's 266. So this is a parameter. And it's known or given to us or assumed. Okay, so then if I take a random sample of people, suppose a random sample of, let's say, 20 human pregnancies, because that's the population, so I'm always taking samples of the population. Pregnancies, how do you spell things? Pregnancies. So suppose I take a random sample of 20 of these 20 human pregnancies. So I'm going to find a statistic that would be the sample mean of these 20 people, these 20 human pregnancies. So then the sample mean of the sample, that would be a number associated to the sample, and that's why it would be a statistic. In other words, a little x bar, that's a statistic, because it's a sample mean, it's a possible value of the sample mean, so it's a number associated to a sample, so it's a statistic. Okay, so let's keep piling on this jargon. So what else could we do? Well, let's also use the big X notation that we learned. So we would also say, so we have a random variable in this problem. So I'll call it X. So it's not X bar yet. So what's the random variable? What's the number? The number is the length of the human pregnancies. So this is a random variable. It takes values, takes different numbers that it can be, and it's what is being studied in this problem. So then when we have a random variable, what you do is you say that it takes values little x, and these are the actual possible lengths of human pregnancy. But now what we're also saying when we're talking about probability distribution is we're taking these values, not all equally, not all possible lengths of human pregnancy are equally likely. For example, 1 day is very unlikely, whereas 266 is the mean, so it's probably very likely. So what we do is we say it takes these values with probability equal to the area under the normal distribution. So 266 plus 16 is 282 to get me to the first inflection point. And then I subtract 16 to get to the inflection point the other way. Gets me to 250. So the idea is this is the mean. This is the parameter. And here I'm just adding and subtracting standard deviations. And then this is all because in the problem we're starting with the fact that X is normally distributed. The problem tells us at the beginning that the length of human pregnancy is normally distributed. So that's why I can say all this stuff here. Okay, so now introducing the big X bar, the new notation we learned. So what's X bar in this context? It's the mean human pregnancy length, amount of time, but for samples now, and because we're doing samples of size 20, we have to include that information. And so this is a random variable. So it takes values, it takes numbers, as it can be different numbers. And those numbers that it can take, those values that it can take, we call little x bar. And let me write it here. So what can little x bar be? It can be those possible sample means, where you take a sample of size 20. But it doesn't take these values all equally likely again. So instead, it takes these values with probability equal to area under this normal curve. Called the sampling. This is the sampling distribution of the sample mean for this problem. So this is the mean of this distribution, and it just always turns out to be the same as the population mean. But the standard deviation is not the same as the population standard deviation. Let me write this up here. The standard deviation is the original standard deviation, which is 16, over the square root of the sample size, which is 20. So it's around 3.577. So if I add that here, I get that. And if I subtract it on the other side, I get that. So this is really adding one standard deviation. This is really subtracting one standard deviation. Okay, so that's really what's going on with all the jargon possible that we've seen. Let me zoom out a lot, see if I can see it all at once. Not really. Okay. So then the idea is the new questions are always asking about this distribution. The old questions are asking about this distribution. And we really are talking about very fancy things, random variables. But the problems themselves you don't have to worry so much about all those fancy things. It won't be so bad, I hope. Okay, so let's just do one example using this distribution just to do some extra practice. So then the types of questions that can be asked always sort of go the same way. It's always find the probability, or it could say, instead of probability, it might say percentage, or if they really want to trick you, proportion, but it's all really asking the same thing. So find the probability, percentage, or proportion of human pregnancies. And then they might say between blank and blank, this could be different numbers. Or they could say below something or above something. But those can be different numbers again. And so what this is really saying, to translate into fancy jargon, this is really saying find probability that your big X, your random variable, that's what these human pregnancies, lengths of human pregnancies are, is between two little x's like that. So what's the probability that your random variable is between two specific values? That means you have to use little x for the notation of the specific ones. That's what this question is really asking. And then these other ones are just saying, find, I could even just say, find the, this is also the same as finding the area between x1 270 and x2 275, which we do with the z-score stuff. This is just saying find probability that x is below a specific value. And then that's just saying find the area below that specific value. And then this is just saying find the probability that your random variable is above some value. So then what we're really doing is we're just translating this question into this area problem for this normal distribution. So there's 266, 282 if you add 16, and 250 if you subtract 16. So then what we're really doing is we are finding this area between 270 and 275 to answer this type of question. And what you're really doing for that is, so I'm just translating the question over and over and over into different things. And then what you're really doing to find that area is you're finding Z1, you're finding two Z-scores for 270, a Z-score for 275, and then you're turning those into areas to the left, and then you're subtracting areas. Same idea for these two problems. You can translate these into areas and do the same thing. So that's all the old stuff. So that's one type of question. And then the other type of question is the new stuff, but it sort of sounds very much the same. So we're still finding the probability or the percentage or maybe the proportion. It always sounds the same, but now it's of samples instead of people or human pregnancies or something like that. It's of samples of some size, which can change. It doesn't have to be 20 every time. It could be something else. And instead of asking for the thing itself, instead of asking for the human pregnancy to be between 270 and 275 or something like that, we're asking for the mean of the sample to be between. But it can be lots of different questions. It could be between two things, it could be below, or it could be above. And then you might even use the same numbers, 270 and 275, let's just say for this. But you might also want a problem that's asking you to find the probability percentage or proportion of samples of size 20 whose mean is below or something or above something instead. Let's focus on the between. So again, what does this really translate to in our fancy new jargon now? This is really translating into talking about capital X with a bar on top, finding the probability that this random variable is between two specific choices of that random variable, which you call little x1 with a bar and little x2 with a bar. And then that translates into finding area.
Okay, so my recording froze mid thing. So this is the second recording that I glue onto the first recording. Works, but I'll repeat myself a little bit. So anyway, we were finding the probability between x1 and x2, and I was going to say that that's the same. So I'm just translating this question in various ways as finding the area between those two. But on this other distribution, where the mean is still 266, because that's the same as the population mean, but the standard deviation is this other thing that we already calculated, 3.577, which I remember came from 16 over the square root of 20, is it? Yeah, the sample size is 20. So finding the area here, so because of this being a standard deviation, that's the first function on the right. You just have to add and subtract that amount. So you do that with this. So translating this question into this area is now asking, well, 270 is about there, 275, not much further than that. Well, actually, much further. So that'd be 270 and 275, there somewhere. So now this question is about finding the area in blue here. Which then, again, I'm just translating over and over, which is really finding the z-score for each of these things. But on this distribution, and then That's how these two areas to subtract. To get the middle area. And doing an area probability below, probability percentage proportion of samples of size 20 below something turns into the same idea, and above something turns into the same idea. And translate it all the way through the same. But finding area below just means that this area would be your answer because that's the area below 270. But finding the area above would be doing 1 minus the area below. Area above. Okay. So that's it for today. I'll see you next time. We'll start on a new similar topic.